Hello and welcome back. We're going to take a look at how we acquire the MonkeyJam software through basic compile and download to the board. So this is enough to kind of get you started. And the rationale behind this video is often when you get sample code, it's nice to have someone talk you through it a little bit so you can understand what's going on. So I'm going to do a little bit of that. So if we come to the MonkeyJam main page, I'm going to scroll down here. Mentions here's some of the materials. Example code is on GitHub. So on GitHub, I've created a release. Right now we are at revision R0, and release R0 kind of has the basic settings to get things to work. Now, if you want to become a contributor, you can. Just got to get a hold of me and leave a comment. If you want to kind of contribute to the main master branch here. Now, a quick note is that to compile the software, you're going to need CodeWarrior 10.5 for Eclipse. At some point, the K20D50 will be embed enabled, and we'll have it on the embed online compiler. Number 2, we're going to talk about in just a second. But number 3 is to mention that the master branch is kind of where the releases are tagged. But I have an experimental branch that I use for my own kind of playground. So if you're ever looking at experimental branch, you might see buggy code, code that doesn't work, code that doesn't compile. It's mainly for me. So master is where you want to be. Now, if you don't know what you want, on the first link, this is what you want. Just you got to get the latest release, and as of this video, it's R0. You may see other releases depending on when you're watching this video, but this will give you a place to start. So what's nice with GitHub, we can just grab the source code, and it's going to download. And now that it's downloading, it's kind of a big file because of all the libraries associated with it, but 12 megabytes. Close that. Now what I'm going to do is, okay, I've unzipped, extracted the folder. So let's just take a quick look to see what's inside. Let me zoom in here. So there's 2 folders, one called MonkeyJam and one called Simsys DSP 3.2. So the Simsys DSP is a DSP library that I use bits and pieces from for the MonkeyJam. And that's its own Eclipse project for CodeWarrior 10.5. And MonkeyJam is the actual software. Now, you can look in there if you want, but we're going to directly import to kind of see what's going on. So now what I'm going to do is I'm going to open CodeWarrior. All right, so I'm going to create a new workspace. I like having multiple workspaces, and CodeWarrior is crunching away here. So by the time you watch this video, you might have a newer version of CodeWarrior, and that's okay. Like I said, we know that 10.5 works, but it should be no problem just to re-import into a newer version. So what I'm going to do is, there's several ways if you've never used Eclipse before. I would really suggest, I have another set of tutorials called the Book of Eli. Now it's focused on the Freedom KL25Z board, but the concepts are exactly the same in terms of like importing projects and whatnot. So in CodeWarrior, here we have our workspace. There's nothing in it, so I'm going to go down to the commander, go import project. That's one of the ways. And we got to do is browse through the root directory. So Eclipse will search through a directory and all subdirectories for projects. So it brought up Simsys 3.2 and MonkeyJam. We need both of them. You cannot build MonkeyJam without this other project in your workspace. Click Finish. It's going to open. Now, you may get some error messages about resources not being found. Just click this and click OK. For whatever reason, I was having trouble in my Simsys DSP setup. Whenever I moved the project folder, I didn't like it. Yeah, because it says references to workspace location. So It's maybe someday in the future I'll fix that, but either way, it's not going to stop you from doing anything. So we're going to go project and we're going to go clean. So what this does is we want to clean all projects, is remove all the binaries. So it's going to remove the library generated for the Simpsons DSP, blow away any of the files from the MonkeyJam in terms of the object files and executable, and just rebuild. Now, the first time you build it might take a little bit because it's got to build the Simpsons DSP library, and there's a lot in there. It shouldn't take you more than a few minutes, but once you build it once, you don't have to build again. Just if you do clean again, you only have to really clean the MonkeyJam, but that's all you have to do. So it's just about done. There's jam test is the name of the output. So here's MonkeyJam. And let's just kind of take a look at the folder tree. So I put everything under sources, and I want to navigate a little bit through the source tree here, just so you know where everything's at. So I like to separate main into its own clean little area here. So here's the main function, and usually the way I set up main is I don't like main to do a whole lot. I want it to run a couple of init routines and have kind of like the main super loop with maybe a switch statement controlling a state machine or something. So in my main routine, you see the first thing I do is I initialize the PLL to 50 megahertz. The K20D50, you can actually bump it up to about 72 if you really wanted to, or 72 and 75. I don't take any responsibility of you catching your board on fire, but it does work. I have a function called init.io. All you have to really worry about at this point is that kind of gets the A to D converter channels, the potentiometers, whatnot set up, the I/O. Init audio process, that actually gets the data converter interrupts working, and the data converter setup working. Then we enable interrupts. Now, I'm going to jump down here. Then I call this function called change patch. So the concept of this example software is we have different patches. Patches are just kind of examples, different settings. So I have a function to switch between them, and I just call this once at the beginning to change to the patch called, for example, here, to be clean. And then in the main loop, we simply switch on the value of that patch and execute code depending on the patch. Now, we're going to look at where the change patch function's at, but let's just look through, a patch. So the first concept I want you to understand is that no audio processing is done in the main loop. The main loop is just there to read potentiometers, calculate maybe some parameters for a processing loop, and that's it. Nothing time critical is in the main loop. It kind of operates on whatever CPU cycles are left over from the audio processing routine, and you don't need many because it's a human interface thing. Hundreds of milliseconds of response time is fine for for turning the pot. So the best way sometimes to understand an API is to look at it. So I have some neat functions here called set pot limit. So there's 3 potentiometers on the board: alpha, beta, and gamma. So when you read those, at the data converter level, you just get integers. Well, I have an interface where you can kind of remap a value that kind of comes out of this interface to whatever you want. So here I'm going to say set pot alpha to 1000, 4000. So what that'll do is every time I want to read the potentiometer, I get a floating point number between 1000 and 4000. It's just a neat way of scaling it. Here I have a function called OD level. That's a gain. I just set to a maximum Q31 type. But here's another example of setting pot limits. So I want my beta pot to go from 0.05 to 2.5 and my gamma from -15 to 15. So this is floating point code. I don't use it for audio processing. I simply use it as an easy way for a user to set up the range of their pots in a nice way. And you'll see why in a minute here. So below that, in each one of the patches, we want to be able to kind of control some filters. So all of the filtering in the MonkeyJam example code is done with IIR filters and IIR biquad. So there's a neat little function here called design audio biquad, which if you simply give it a pointer to the structure of the IIR filter, in this case what's called shadow coefficients, you kind of tell it what you want. In this case, a biquad low shelf. You got to give your sample rate, and then you just give it some parameters, F0, Q, and dB gain. And notice how I just read the pot and dump it in the parameter, and it designs the filter for me. So this function, and let's just go to the declaration, is an IIR.C under DSP. All I did was, there is an audio cookbook out there, an audio, let's see if I have the link in here. I may not have the link. Yeah, here it is. From Music DSP, an audio EQ cookbook for biquad filters. I just took that and implemented some IR processing routines in a filter computation engine, if you were, to design filters. So basically you pass it the coefficients you want to update. There's a lot of different filter types. I'll let you look into that, and you just kind of fill in these other parameters. I just, in my main routine, tie those to potentiometers. So here we can, for to be clean, our frequency where things are happening is on alpha. Beta is the Q of the filter, and the dB gain or cut is on gamma. And you're going to see, just by playing around with one simple filter, you can really change the tone of the guitar. And in the sound samples, I'll try to make that apparent, that you don't need 20th order filters on a guitar. It's absolutely ridiculous to think you do. You can really control tone with just a handful of high precision filters. So I have another filter. There's two filters, IR0 and IR1. 0 is to control tone, and this one is kind of simulating a speaker with a roll off of about 2.5 kilohertz. And that's about it. Now, one thing I'm going to point out, we're not going to go into a ton of detail, but I want to point out is that when you're playing with IR filters, it is possible to put the coefficients in a state that the filter is unstable. It's called putting the poles outside the unit circle. Well, that can happen a lot of different ways. So when you're designing a filter and you're updating coefficients, it's important that you update the coefficients in what's called an atomic manner. It's all in one. You don't want to update the coefficients during the when the audio processing routine's running. And this is important here because the audio process routine in audioprocess.c happens in an interrupt routine. You'll get interrupted when you get a new sample to process. So you could be in the middle of updating coefficients in process audio, which is bad. So the way the filters are structured is that there's a set of primary coefficients and what are called shadow coefficients. What we do is we update the shadow coefficients in our foreground routine, and then I have an update flag right here that will flag the processing routine to copy these coefficients in a kind of an atomic manner so we don't mess it up. So there we go. That's it. And for the overdrive patch, it's almost the exact same structure, except the filters are a little bit different. And all the other magic is in the processing routine. So that's the main loop. There's nothing else. So really, once again, the review, we change into our current patch, and then in the main loop, this main infinite loop, we look at the current patch and figure out, well, what do we want to do with the potentiometers? If for what do we want to do with the potentiometers depending on the patch. Now, I said this operates at its own rate. It's not necessarily a super fast rate. It's just fast enough for the user interface to work. We use whatever CPU cycles are available when we're not processing audio. Now, the other key file I want to show you just for playing around is an audioprocess.c. I'll take you right to the function. So, let me expand that. Audio process will get called every time there is a new set of samples available. Now, MonkeyJam is a sample by sample processing engine. It's not block by block, as we discussed in the kind of intro videos to signal processing. This way, we have the only latency we have is one sample, which is really nice. So, the only thing the audio process does is it first looks at there's an I/O there's 3 sets of I/O on the board for switches and LEDs. There's one called I/O delta. Well, I/O delta I have hooked up on my board, essentially a switch. And if the switch is closed, it gives me a 0 value. All I do is I pass through what I measure, and I use this for debugging as well. This is a really nice debugging feature. So you notice what we have to play with is every time audio process is called, we get a sample for left in and right in. They're Q31.2 values with the actual audio data shift all the way to the right, the 24 bits to the right. Well, for the audio subsystem to work, when you're done with audio process, you always have to update 2 variables, left out and right out. So I just pass them right through. Now, for me, I don't usually do anything with the right channel. I compute it on the left coming in and dump it over to the right because it's guitar and it's mono. And we don't have a ton of horsepower with the K20D50, so I just kind of process mono, which is fine for guitar. So if I/O delta is not closed, then we come to the else case. In this, we simply look, if we're actually processing audio, what our current patch is, and then do something different depending on our patch. So, for example, I have a pass-through patch that does the same thing as this switch. I have something called the sine test, where if you turn this patch on, it simply outputs a sine wave. Simple as that. In the video where I show how to model tube overdrive, I have one called overdrive sine demo test, and here I compute a sine wave, and then I run it through the soft overdrive, so you can see how that works. Now for the actual sound samples, I have the to be clean and overdrive. Let's look at to be clean here first. So what to be clean does is that the first thing the audio process will do is say, has my main loop told me to update my coefficients with a value greater than 0? If so, I simply copy my shadow coefficients into my real coefficients. All right. And it's as simple as that. Now you notice with IR1, same thing. And I just found a bug in release 0. This should be a 1. So after that, what I do is to do the processing, I have an intermediate variable I just call signal, and it's what I use to pass the data around. So I say left in equals, or signal equals left in. I have some functions that, for example, compute IIR. You give it the IIR, the data struct, the signal in, and you pass a pointer to the result. So I just use the same variable to pass the data in and get my result. Then I have my soft overdrive function. And the idea here isn't to hard clip, it's to provide a very soft clipping just to add that tube-like compression. You may get a little tiny bit of edge on it, but that's it. And then we pass it through our final filter. Now this here this is an ARM intrinsic, is that if for whatever reason you're beyond the 24 volt span is to limit it, if this happens, something's really wrong in your filter. You had way too much gain, and you're outside of the 24 bit range. But this will sound better than a wraparound if you go beyond 24 bits. Lastly, I just take the signal and dump it into left out and right out. Okay, simple as that. Now, for patch overdrive, it's really the same structure, except that I add the left and right in. I compute a IR filter. I have a different function called hard overdrive, which uses a different lookup table for the arctangent function. That's a lot harder. It'll clip a lot quicker. I should say clip. It'll overdrive quicker. I have my speaker simulator filter, and then I dump out the result. So at that point, we're done. So now to run this software, what I'm going to do is we already did a build, but I'll just do it again. I did fix that little bug there. I'll re-push that up to GitHub. All right, we get a warning from the SimSysD. That'll go away eventually. Now, in case, for whatever reason, sometimes whenever I move these projects the debug configurations get messed up. So what I'm going to do is I'm going to say debug configurations. We're going to reset it up. And we want a Code Warrior debug configuration. And notice it's just going to make one for MonkeyJam. It says here's the project. We can browse for, it already found the L file. I'm going to choose the Open SDA interface. That's important because that's what's on our board. We'll just go debug and see what this does. So this is real time. This might blow up. I don't know. Nope. It looks like I have my MonkeyJam connected. It's downloading. And here we go. We're downloaded and I can hit go. And, now the program is running. So I'll hit stop. Now, if you want to play with the different sounds, so there's to be clean, all you got to do is already have it set up. If you do a change patch to overdrive, you'll get the overdrive effect. Now, you have a basic framework. You can start playing around. Maybe you want to do chorus, flange. I have some work in my experimental branch, but I would recommend that just write something yourself. Now that you have a basic framework for playing around with guitar signals, it's up to you to come up with something that sounds really cool. So that'll be it for this video. I hope this was instructive. So come up with some neat, patches of your own, or maybe rewrite the code. Maybe you'll make it a lot more efficient and run faster. So just let me know, and I'm always happy to see what people are doing. So that'll be it, and tune in for another video another time.